All right, we are heading into 8.3. The way it's always presented here, this is something called logarithms. Kind of funny to say, but logarithms are exponents. The best example for logarithms is something called a Richter scale. Richter scale is the magnitude, how big an earthquake is, and they reported just the little news thing right here. This little right here is 6.0. That is a Richter scale measurement of a earthquake, and we measure them by this. Let's see what else I want to say. But this is really a number on an exponent, or actually we calculate by using logarithms. So if you say something is a 6.0 earthquake and something is a 7.0 earthquake, that 7.0 earthquake is 10 times bigger than the 6.0 earthquake. And we'll sort of see how that is in a little while, okay? But just so we see it here. Okay, anyways, let's go to the table. And so although the size of the numbers of the table do not seem to be very different, the intensity of the earthquake can be measured very. For example, the 1989 San Francisco earthquake was more than 10 times stronger than the 1999 California Columbia quake. They forgot one. So if you look on page 513, if you have the textbook there, they forgot the most important one. They forgot the Kalinga earthquake of 1983. Right? It was a 6.2 earthquake. So this 6.2 earthquake and the 7.2 earthquake in Japan, this earthquake here was 10 times stronger than this one, and that's what these numbers mean. So if you go from 6 to 7, it's the intensity of movement. That's what they're measuring. What is a 0? 0 is flat out no movement at all. Actually, no. 0 is the smallest, tiniest amount of movement that we can measure. And we do have measurements of it. There's measurements all across California. It's just this big sensor pole that's just dug as far as we can stick it into the ground. At Fresno City College, if you go to their, I think it's the first floor, you walk in and that's the sort of the geology department. They do have a seismometer right there. And so that means underneath the seismometer, there is a big long pole, basically, with a little sensor on the bottom, and it's just a big old humongous hole dug the bottom of the building, go as far as you can go down. So my question to you guys, how many earthquakes per day do we have? Yeah, sometimes in the 50s, low 50s, sometimes in the top hundreds. But they are usually like a 1.0, 2.0. So there's no feel to it. But the other thing is at Fresno City College, they keep track of it. I don't know who changes the paper every single day, but there's a paper roll, and it sort of spins in a circle, and there's a little dial, kind of like lie detector test. And so there's a little dial, and all it does is just sort of, whenever there's a shake, it goes, and then and I don't know who does it, but sometimes they'll actually write in like 1045, 2.1 quake, and then they'll give the duration from this time to this time, and there's like little pin markings on it. Anyways, that was kind of cool though. Like, dude, never knew that actually happens. All right, in this section we start our work with logarithms, which will give you an understanding of the Richter scale. So let's begin. Notice from last time, y is equal to b to the x. Wasn't that our little definition of something? That was the exponential function, right? Let's go a little bit more in depth. First of all, notice on the last two sections here, there was never a time where the base was a negative number. If there's a negative number in here, it just doesn't make sense. So you can have numbers that are whole numbers is fine. Fractions are fine, right? Like 1/3, we did 1/3. 1/2 is fine, 1/4 is fine. But you cannot have negative numbers in here. Next is that b also can't be equal to a 1. That's the other condition. So this b value has to be positive and not equal to 1. Just real quick here, if it is equal to 1, what's happening? It's just a regular line. That's why. It's It's not an exponential equation. That's the problem. Okay, now let's go back. I'm sorry, now let's think about this here. Let's switch the x and the y. That's what I want to do. So the y becomes the x becomes the y, and there it is. Voila. Kind of cool, right? No, not cool? I think cool. This right here is now called a logarithm equation. Now the only problem is, see how this y is not solved for? We like y's to be solved for, right? And so we're going to have to sort of just change the whole form around. That's what we're going to have to do. So this is the number, this is the base, and that's the exponent. So we have to sort of keep those in mind. Number, base, exponent. Definition: number, x, base is b, y is the exponent. So the expression, there it is right here. It's y equals log base b of x is read. Y is the logarithm to the base of b of x. And it's equivalent to this right here. This is the form that we want to use right here. So y equals to log base b of x. That guy is the same as this guy, but now solved for y. Cool. Okay. So, does this make sense? The logarithmic function is the inverse of the exponential function. We'll get into some weird stuff here in a bit, but just for us to know that. Exponents, logarithms are just inverse functions of each other. That's why we took a whole section 8.2 to look the whole concept of what an inverse was. So now we're going to have to finally look at it. All right, let's go to the different forms here. So 8 is equal to 2 to the third. We can write the same exact form as log base 2 of the number 8 is equal to 3. And again, everybody agree 25 is actually 5 squared? We can write it like this, and that's fine. We can write it as log base 5 of 25 is equal to 2. And sometimes if you're not sort of used to logs, what you're going to do is you're going to do this here. What exponent do you put on 5 to give you 25? And it's 2. That's kind of what a log is. Going back to the first one, what exponent do you put on 2 to give you an 8? 3. Okay, good there? Just want to sort of get you guys used to this here. Again, there's some weird ones in here too, but all it is, we're just changing forms, that's all. So 1/8, 2 to the negative 3. Log base 2 of 1/8 is equal to negative 3. All right, and the general form, it is r is equal to z to the s, therefore we have log base z, because that's our base from the previous number, of r is equal to s. So now, notice that this one here is solved for r, and this one here is solved for s. That's exactly what I want. So in a sense, this one is solved for the y value, this one's solved for the x, or this one's solved for the x, this one's solved for the y. I can solve for the other variable right away. That's what I want. Okay, so let's practice sort of just changing forms first. So convert to exponential form, and then solve for x if you can. All right, probably easy way to sort of do this here, and I've sort of found, is this little, sometimes people call it around the world, sometimes people call it a hook, whatever you want to do. Just we're going to go from the base, we're going to go to the exponent, and then we're going to go to the number inside. Cool. All right, let's go for it here. So what's my base? 2. What's the number? Or what's the exponent? Sorry, what's the exponent? 3. Remember, exponent is the number equal to. And what is the number? Yeah, so the number that was inside the log now becomes outside of that. That's kind of what I want to see there. It was stuck inside the function. Now it's actually what it's equal to. So I think we got it right. Something called x equals 8 after you simplify it. All right, number 2. All right, hopefully, let's see, base is 2. The number, or the exponent is, I'm sorry, base is x, sorry. The exponent is 2 and the number is 5. Good there? And simplifying this, square root both sides. And just a quick little question here, should I or should I not put a plus or minus? I'm gonna not put a plus or minus because what's my restrictions for this base? Can't be negative, right? And it can't be 1. That's my restrictions for the, because that was my restrictions for the base for the exponential function. Can't be negative. So no plus or minus needed. The answer is just the square root of 5. So technically what we're saying is what exponent do you put on a square root of 5 to give you 5? And the answer is 2. Alright, gets more complicated, of course. And this is just a quick quick way to sort of go back to review a little concept from algebra. Okay, so my question to you, can we figure this out right away? Can we know what x is right away? So what exponent do you put on 9 to give you 27? Ooh, no fun, huh? Because there's no multipliers of 9s to give you 27, right? Ah, okay, so let's do this here. So what's my base? 9. Exponent? And number? Okay. So if you took algebra 2 in high school, then you know how to solve this problem here. Oh, hold on. If you took algebra 2 in high school and you stayed awake during the class, then you know how to solve this problem. So exponential functions or equations could be solved if we can get the same base on both sides. So what's the base for 9? 3, that's right. 9 is really 3 squared, right? And that is actually being taken to the x power. On the other side, what's the base for 27? All right, 3 as well, so that's actually 3 to the third. All right, and then something happens between the 2 and the x. What is it? All right, we multiply these two, right? 2 times x, how about a 2x? And how about the same thing on that side? Okay, if we can get equations with the same exact base, we cancel the bases and we only work with the exponents and solve that. And that's okay too. So divide by 2, and how about we get ourselves 3 halves, and that is the final answer. Okay, so you guys will see some of those to work off on the homework. Again, just realizing if you can get the same base, you're in good shape. All right, let's move on to the graph here, and then we'll move on to identities here. So how do we graph this exponential function? Well, we actually did already. After you get used to the logarithmic functions here, then you'll be able to graph them straight. But I think at this point in our thinking, here's what we're going to do. We're going to graph the inverse of it, and then we're going to switch back the points. Good there? So let's go for it here. If we're going to graph the inverse, let's get the inverse. So let's switch the x and the y. And can I change forms here? I want to switch this into exponential form. What's my base? What's my number? I rewrote it again here, but my base is 3. What's my number? Oh, sorry, what's my exponent? X, and my number is y. Switch it around just a little bit here just to make sure. There it is. I'm going to graph y is equal to 3 to the x, and I think this is the 3rd time we're going to graph this function. So you better know what this looks like already. Something about -3 and 1/27, is that right? -2 and 1/9. -1 and 1/3. 0, 1. 1, 3. I think those are the numbers we used, right? Again, look back at your notes if you need to here. Okay, but I'm not going to put lines on this because that's not what I'm trying to graph. I'm trying to graph just log base 3 of x. So no lines connected yet on this one, but I'm going to take the inverse coordinates. Can you take the inverse coordinates of those? Did it before, why not? So now we're going to graph in blue, we're going to graph y is equal to log base 3 of x. We're going to graph the original function now. So 127, negative 3. 1/9, negative 2. 1/3, negative 1. 1, 0, 3, 1. Alright, and now I'm going to connect the blue dots together as the same one. That's what I want. I want that blue line there. In high school when I used to teach it, yep, I used to make the students erase the red dots. Just keep the blue line. Love it. Okay, and again, the book is just trying to illustrate a point. You don't need to put the dashed line down. Just trying to illustrate the point here. That's what we're doing, is we're just taking the dots here and make them symmetric across this little line right here. So top left hand corner, bottom right hand corner. That's all we're doing from these points. Okay, so that's the graph. We'll at least have a graph of it. And the example problem in the textbook, actually it graphs for you y is equal to log base 2 of x. So you can kind of see a little difference there as well if you need to. Okay, let's move on to some identities. We're going to get a whole bunch of identities here. In fact, the rest of the chapter is kind of building properties and building identities into here. So the first two. And let's build to it here. Again, the way we're going to build this is going to look at numbers themselves. And if the numbers work out, it's almost like this. If the pre-algebra stuff works, then the algebra stuff has to work. Okay? And so let's just illustrate this here. So I have a base called b, and then I take the log, but actually I put it into the exponent. So it's base b to the exponent of log base b of x. It's equal to x. So let's see, let's gonna put in some numbers here, and let's see if it works out. All right. Again, these are from my brain, okay? This is I'm going to put a base of 5, then I'm going to put log base 5 of 25. My question is, what will this be? Well, let's simplify as much as we can. Let's do the exponent first. Just this stuff. Forget about the base of 5 here. Just log base 5 of 25. So what exponent do you put on 5 to give you 25? 2, right? It's 5 squared. So if I do that, this just becomes 5 squared. Final result is, hey, 25. So why do all that work when actually I can go from here straight to here? And that's kind of what this rule illustrates. Again, if you use any kind of numbers whatsoever, it doesn't matter what you use. It's going to be the same thing here. How about 3? Let's use 3. 3 log base 3 of 81. So what exponent do you put on 3 to give you 81? Cecil?
4.
No. 4. Good. Okay. 4. Right? So because 3 times 3 is 9. Times another 3 makes 27. Times another 3 makes 81. So now it's 3 to the 4th. But what's 3 to the 4th? 81. So, okay, a toughy one. Ready? 7. Log base 7 of 34. Answer is? Totally possible. Can't use your calculator. See See, this is where we're getting to the abstract. The answer is, anybody? No, no, nope. Let's see. I'll give you a hint here. Follow the pattern. Tamba? No, follow the pattern. We had a pattern here. This is a pattern here. There's a pattern here. And the pattern is?
The fifth power.
Yeah. Not power, but pattern. I didn't want you guys to follow the pattern. We're getting somewhere. We're getting somewhere. All right. The answer is? So, well, that was the pattern, right? 81 is here, 81 goes here, right? 25 goes here, 25 goes here. Okay, so now we're ready to the abstract pattern. So b, log base b of x. What is the answer here? X. So this intermediate step doesn't matter because you know whatever this exponent is going to be, if you take 7 to that exponent, it's still going to give you back 34. Cool. Okay. Okay, the other way of viewing it, it is the base. If the log isn't, let's see, I'm going to say this. If the log is in the exponent with the base of the same base that you have on the bottom, the logs cancel and the base cancels. So good? Again, sometimes you probably will start doing that on the properties here soon. Okay, the other one here. So again, we're going to do sort of the same pattern here, okay? So watch out for number 3. Don't let it trip you up again here. So, again, from my brain here, log base 5 of 5 to the 3. What is 5 to the third power? 125. You got it. And then what is, let's see, what exponent do you put on 5 to give you 125? 3. We good? All right, let's go with log base 2 of 2 to the 4th. Well, that's fun. Anybody, what is 2 to the 4th? Good, good. Is it 16? I think. Yep, 16. Okay. What exponent do you put on 2 to give you 16? And we get 4. Okay. The fun one step here. Da-da-da. I got you this time. 28. Okay. Didn't get you this time. Okay. Okay. So then, log base b of b to the x. The answer is just x. So again, if you have log with a certain base and you're taking powers of the base inside the log, that base in the log cancels. All right. Got a few people writing it down. Go for it. Okay, cool. Let's go for it here. Again, just a few practice problems here to go. Simplify the following expressions if that is true. So this one, you actually don't even need to use the properties because they're so easy, but I just kind of just practice the properties here. That's what we're going to do. So 27. Oh, you could also say this here. What exponent do you put on 3 to give you 27? 3, and you're done, right? But I just want to just sort of see. Let's make this into the same base. So log base 3 of 27 really is log base 3 of 3 to the third power. And the log base 3 and the base of 3 will cancel, leaving you just with 3. Not a good example from the textbook. Too many of the same numbers inside that problem. Okay, so 1,000. 1,000 is really what? 10 to the 10 to the 10th? I don't think so. 10 to the second power, 10 to the, that's going to be 100. Cool. Yeah, we heard it out. It's third power, right? 1,000 really is 10 to the third power. And then those cancel, leaving us just with a 3. Okay, and this one, of course, is what's the exponent on that 6 over there? Hey, there's just a 1 there. So this is log base 6 of 6 to the 1, technically. And the answer is just a 1. And again, do you really need to do this? We're just practicing the property. Many times you look at this and just say, okay, hold on, 6 to what power gives you 6? And you get that number right away. All right, 2 more. D is a little tricky one. Cool, good. Okay, 1. This is so interesting. So 1 is really what base to what power? Or 3 to what power? Yeah, a 1 is actually 3 to the 0 power, right? And if that's the case, then we get ourselves a 0. Or again, the other question is, what exponent do you put on 3 to give you 1? It'd just be a 0. Ooh, this one we gotta go from the inside out. Let's see what happens here. So let's simplify. I think you guys are sophisticated enough here. Can you simplify the stuff inside the parenthesis? What is that gonna give us? That's going to give us a 1, right? What exponent did you put on 8 to give you an 8? That's a 1. So that's going to be log base 2 of 1. And then what's the answer here? It's 0. Cool. All right, and the application of this good stuff. And of course, let's go back to the Richter scale here. So, as we mentioned in the introduction, one application of logarithms is the magnitude of an earthquake. If a earthquake has a shock wave, t times greater than the smallest shock wave we can be measured ever on a seismograph, then m is our magnitude. And it's measured by this formula right here. Kind of fun. Well, pretty simple formula, isn't it? I think so. Okay, so when we talk about bless you. When we talk about a shock wave of a earthquake, really we're talking about how, it's called amplitude, but how big it was comparatively speaking. All right, let's say the discussion: an earthquake that produces a shock wave that is 10,000 times greater than the smallest shock wave we can ever measure in a seismograph. It actually will have a magnitude of, and then again, all we do is we plug in the 10,000 for the t. And so that earthquake actually has a Richter scale of 4. But 4 just measured 10,000 more movements than we can ever measure. Or the least amount of measurement. Okay, so let's go to number 6 on our. If an earthquake has a magnitude of m is equal to 6, what can we say about the size of its shock wave? How much movement was there compared to the smallest amount of movement we could measure? And let's plug it in. And that's going to be a 6, so that means it's going to go here. This one's a little different than the example, because now we actually have to go back and figure out t, because we were given t first time. So hold on then. Notice the t is caught inside the log, right? It's stuck there. There's no way to get it out except if we change forms. So let's see if we can change forms. Now what is my base? 10. What is my exponent? It's the 6. Right, and the number is t. So what is 10 to the 6th power? Yeah, it's going to be a 1 with 6 zeros behind it. 1, 2, 3, 4, 5, 6. Cool. So that's a million, right? So that means a Richter scale of 6 means there is a million times more movement than the smallest amount we can measure. Cool. So the Kalinga earthquake, 6.2. It was a little bit bigger than that. And again, of course, why do we do that? Because if you can say category 3 or 4 or 5 or 6, you can have a idea what that would be really quick here. You can sort of scale the numbers. All right, so that is the end of 8.3.